On behalf of 24houranswers.com, I welcome you to today's lesson. In this video, we're going to look at an optimization problem that deals with minimizing the distance on a curve. Let's find the point z on y equals x squared that is the closest to the point negative 18, 0. Also, find this minimum distance. So let's look over in Desmos to get the idea of what we're really trying to do. I have this green point here, and I'm going to call that point z. We're trying to find some point z that's on this curve y equals x squared. So as you can see, z is staying on the curve. But where on this curve is z the closest to negative 18, 0? That's what we want to find. Obviously, way up here, z is much farther away from negative 18, 0 than it is, say, right about here somewhere. And it looks like somewhere in here is where z is going to be closest to this point. That is our goal, is to find this ordered pair, and then we also want to find the distance between those 2 points. Since we're talking about distance and we have some points and curves, hopefully the distance formula maybe is coming to mind, and we definitely want to use this formula. As a matter of fact, this is the formula that we're going to be finding a derivative of because we're trying to minimize the distance. We got to have 2 ordered pairs, a x1, y1, and a x2, y2 to plug into this thing. However, well, we know one of our points is negative 18, 0. I'm going to let that be my x1 and y1. And this other point z that we're trying to find on this curve is some x2 and y2. However, take note of this, x comma y. That's 2 different variables. If we take into consideration that z has to lie on this curve, then y is going to be x squared. So instead of us having x comma y, since y is equal to x squared, let's replace this y with an x squared. So now we have our x1, y1, the point that's given, and we have some unknown point z. That's an x and a y, but we've labeled it as x comma x squared, and again that's because the y value is equal to x squared. Let's substitute these into our distance formula, and then let's prepare to do some calculus. So take note of what I did here. The square root around all of this stuff, I just wrapped the whole thing in parentheses and raised it to the 1/2 power. That's taking care of the square root. Now if we take x2 minus x1, that's going to be x minus a negative 18, so that becomes x plus 18, don't forget to square it, plus y2 minus y1. So we have x squared minus 0 all squared. And again, all of this stuff is wrapped in those outer parentheses, raised to the 1/2 because we are taking the square root. Now let's do a little bit of algebra to simplify the inside here. We're going to take x plus 18, we're going to square it, and then we're just going to add x to the 4th because x squared minus 0 squared is x to the 4th. And that's exactly what I've done here. X plus 18 all squared is x squared plus 36x plus 324, and then we have our plus x to the 4th. Now we're ready to find the derivative of this thing, because we want to find a minimum. And when you're dealing with calculus, to find a maximum or a minimum, we're going to find the derivative, we're going to set it equal to 0. Therefore, d prime is equal to, let's pull the 1/2 down, applying the chain rule to this piece. So 1/2 gets pulled down, we leave the inside alone. Now don't forget to subtract 1 from your exponent, so that's the negative 1/2 power. Now we have to come back and multiply by the derivative of this inside stuff. Again, we're applying the chain rule here. So the derivative of the inside is 2x plus 36 plus 4x cubed. And the reason why is because the derivative of 324 is 0. So really I'm just taking the derivative of these 3 pieces and writing it down there. So here's our derivative. Yes, it does look a little bit messy, but what we can do is we can shoot this stuff here to our denominator since we have a negative exponent. So here it is cleaned up. We shot this stuff down to the bottom with a positive 1/2 power. My 1/2, that's an understood 1 up here over 2. And this is our numerator. And as a matter of fact, the only way that this rational expression we have here can be equal to 0 is if the numerator is equal to 0. Granted, that does not cause any undefined values in our denominator. Basically what we have to do here is set the numerator equal to 0 because that's the only way a fraction can be equal to 0. is if its numerator is equal to 0. And as long as that value of x does not cause any issues in our denominator, meaning we're not going to have a 0 in our denominator, we're good to go. So that's exactly what I have right here. Now, this thing does not factor nice. Sure, we can pull a 2 out of this, but that's not going to help us factor a cubic with a linear term. So let's go to the graphing calculator to find the value of x that makes this equal to 0. Just one note before we graph this function on the TI-84. If you could not use a graphing calculator to find the value of x that makes this equal to 0, you could explore options such as the rational root theorem and synthetic division. There's nothing wrong with doing that, but for sake of time, I'm going to resort to the calculator for this. So we have our function typed in, pressing graph. We have an x-intercept, which is our 0, and it looks like it's occurring when x equals -2. We can verify this by finding the 0, a left bound such as -3, and a right bound such as -1. Pressing enter on guess, we do have a 0 at -2. So therefore, when x is equal to -2, this numerator is equal to 0. It would be helpful to go back and plug -2 into this denominator to make sure that we don't get a 0 down there, and I'll go ahead and tell you we do not get 0 down here. So this is the value of x that's going to be helpful in us finding our point z from the beginning. Now remember, our function was y equals x squared. Since x is -2, if we plug -2 into here and we square it, we get a y value of 4. Therefore, -2, 4 is going to be that point z that is closest to -18, 0. And if we look, this is the location of -2, 4. And I'm just going to cut off the z so that you can see that's where -2, 4 is. It does not look like it's the closest point to -18, 0, but it is. And the reason why that does not look like the case here is because of our scale. Our x scale is different than our y scale, so that can throw things off. If I were to press this home button on Desmos to zoom to default, that's going to scale the x and the y the same, and here's our -2, 4. If we zoom out, notice now when everything's scaled the same, that point does appear to be the closest, whereas these points that we thought we had at the beginning way up here, they are definitely farther away from -18, 0 than -2, 4 is. So keep that in mind when you're looking at a graph. If your scales are different, looks can be deceiving. But hopefully you do see here, that is the closest point on the curve y equals x squared to -18, 0. And to finish things up, we need to find that minimum distance. So let's take this x2 and this y2 value that we have found. Remember, we had it right here. Let's plug that into our distance formula to find our distance. And you could take it and plug it back into here if you'd like. As a matter of fact, we can apply a shortcut since distance is equal to this function here in terms of x. Let's plug in the -2 into all these values. Plugging in -2 into the stuff on the inside of the parentheses is 272. That is getting raised to the 1/2, so we do want to take the square root of 272. Now you may need to simplify this radical. So an approximation is around 16.5 units, but again, simplifying this radical, if we take 16 times 17, 16 times 17 is 272. We can take the square root of 16, and therefore we have 4 square roots of 17. This is our exact distance between the point -2, 4 and that other point that was sitting off the curve, -18, 0. And we can verify this in the calculator as well. Notice the square root of 272 is the same thing as 4 square roots of 17. So here's our point z, and here's our minimum distance. And there you have it, a very common optimization problem where you have to find some point that lies on the curve, and you want that point, in this case here, we called it z. You want to find the point on the curve that is closest to some other point that is not on the curve. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.